Time-appropriate greetings, ladies and gentlemen. This is Sean McBride, your graduate teaching assistant, and I'd like to welcome you to Laboratory 5. So today we're going to be doing some additional practice with regards to multi-threading in Linux and the use of the pthreads library. We've been covering this a fair amount in class during class exercises and past laboratory exercises. In this lab, we're really going to be taking a look at what happens when multiple threads interact with shared resources. And we're going to examine race conditions and figure out how to kind of think about critical sections and then how to protect those critical sections with mutexes, a pthread construct that provides mutual exclusion. So mutex is short for mutual exclusion. So on my screen, I have two shell environments. On the left is a purple environment, and that environment is single-threaded. And on the right is environment with a black background, and that is a multi-threaded environment. And you might be wondering, what are this ASCII art that you see in the background? Well, today, one of the lab exercises that you're going to be performing is basically attempting to protect the elf magic from being devoured by the zombie children. And I'll show you what that means in a little bit. But first, let me just demonstrate to you the difference between these two environments. So I can run the shell command ls cpu on the left-hand side. And we can see a bunch of information about my processor. But notice here in the area that I've selected that we see threads per core 1, cores per socket 1, sockets 1, NUMA nodes 1. And that's because this is running on a multipass virtual machine that has been specifically limited to having one virtual core. In contrast, on the right-hand side, this is a Linux environment running under the Windows subsystem for Linux version 2. And this basically offers a pass-through capability where the Linux guest is able to have full access to all of the underlying cores. So we can see here that I have 16 cores visible. Really, I have 8 physical cores, 16 virtual cores on this processor. But just to kind of show the difference here, so on the right we have a multi-core system, and on the left we have essentially a single core system due to how the virtual machine is configured. And this is significant because on single core systems, generally, the problem of race conditions just really aren't as prevalent, right? Because a single core can execute just one thread of execution, and just that physical limitation in and of itself ends up protecting against most forms of race conditions. And so we have a program here, which I'll just open pretty quickly, race.c. And in here, we basically can see we're starting multiple threads and then joining them. But within those threads, we have these two functions that get executed. And thread 1 prints over and over and over this elf magic, elf magic, elf magic. And thread 2 prints over and over zombie children, zombie children, zombie children. And each of those execute until they reach max iterations, which is set to 1000 right here. And all these strings are getting printed out to a file called out. And so we can see I've already run this program and it's produced this file out. So let's go ahead and take a look at what that looks like. So we can see zombie children printed over and over again. We scroll down and then we see elf magic, and notice that all the zombie children ran to completion, and then after the zombie children were done, elf magic began to execute, right? And ran to completion. And so to take a look back at the race condition file here, we have one thread with this body of execution. We have another thread with this body of execution, and we essentially saw that these are serialized, right? So this function ran on a particular thread of execution, and then this one ran. That might seem a little weird because we have these multiple P threads, but remember we're on a single core system, and a core can only run one thread at a time. So in this case, we spin off this thread here, and it executes thread 1 function all the way to completion, and then this thread here runs. Both these threads are created. It's just the scheduler runs them one at a time. So let's take a look at how this behaves on a multi-core system. Remember here on the right, this is multi-core. We have 16 cores here. And so as with the other side, I've built and run the program. So we can take a look at the output here. And here we can see, I'm already like halfway through the program. At the beginning, at the top here, we see elf magic, right? And it looks fine. But eventually, you can start to see some interleavings here. So this looks similar, and some of these interleavings can be kind of a little difficult to spot. So here's a good spot here. So we can see elf magic, elf magic, elf magic, zombie, elf magic, children. And so we can see here zombie and children have all this elf magic stuff in the middle. So these interleavings kind of signify that in this case, since we have multiple cores, we're executing both threads of execution in parallel. And because both of these threads of execution are writing to the same file descriptor, we have these strange interleavings. So throughout this lab, you are essentially going to be investigating this and using mutexes as a way to basically protect the critical section, which in this case is all the prints to that shared file descriptor. So I think this is going to be a pretty interesting lab for you. And one thing to keep in mind is that this lab is designed really for teamwork. And what I mean by that is that in the lab guide, there are a number of essentially roles that are assigned to different team members. So the lab guide assumes that there is a team of essentially 4 people, and each person on that team has a particular role: architect, threadripper, locksmith, and keymaster. And so if you are taking this asynchronously and remotely, then probably you're just going to have to perform all of those roles yourself. So that means quite a bit more investigation of the man pages. If possible, and you've got the ability to coordinate with other students that are taking this lab remotely and asynchronously, try to find a synchronous time to get together and complete this. And I think you'll get a lot more out of the lab taking it that way. But if you can't, then just assume the responsibilities of all those roles and read all the assigned man pages. But please do make sure that you focus on answering all the comprehension questions, because I know that generally when you're working with other folks, there's a little bit more back and forth, and that generates a little bit more discussion. So if you're working individually, you just have to work a little bit harder at making sure that you're thinking about things as much as possible. So good luck, and please let us know in the Discord channel around the world if you have any questions or issues. Thank you very much and have a great day.